Good day, everyone. My name is FANG and I'm from Xuzhou University of Technology. Thanks to the Committee of Simultudes 2021 conference. I'm really honored to have this opportunity to have my presentation for my paper. And please don't be hesitate to contact with me by the email shown on the screen if you have any problem. My paper is named Application of Cascode Gallium Nitride HEMT in LLC soft switching converter, and it consists of 4 parts. First of all is introduction. In this part, I will explain the reason for what I do this research and what we can do for industrial area. In the second part, I will show you the LLC resultant converter principles. In the third part, I will show you how the experiment was accomplished and the analysis of test data was done. At last, the conclusion is driven by the experimental verification and data analysis. So, let's start. As the essential component of modern industry, China also attaches importance to the development of wide bandgap power devices, the advanced manufacturing process of essential core components, and critical basic materials urgently needed by households, appliances, and other industries have been popularized and applied. ZVS zero voltage switch is realized in LLC resultant soft switching converters on the primary side and ZCS zero current switch on the secondary side. The loss of the converter decreases and the efficiency of the converter is improved. Then let's talk about the LLC resultant converter principles. Figure 1 shows the topology of the half-bridge LLC resultant converter, which mainly includes 4 parts. The switching network generates the square waves. The resonant network consists of resonant capacitor, resonant inductor, and excitation inductor. The rectifier and the filter network is composed of a high-frequency transformer with a middle tap, rectifier diode, and filter capacitor. The switching network consists of main switches Q1 and Q2 generates a square wave voltage with a 50% duty cycle and adjustable frequency through complementary conduction. The data time is inserted between the complementary conduction of Q1 and Q2 to prevent the bridge arm from passing through. Thus, ZVS on the primary side is realized. The impedance of the resonant network changes from the charge of switching frequency, and the output voltage is adjusted with the switching frequency. The rectifier diodes D1 and D2 are full wave rectified, and the output voltage is filtered by filter capacitor. When the converter switching frequency F works in different load ranges, the system operates in 3 states, and Figure 2 shows the waveforms of the converter working in different switching frequency ranges. LLC resonant converter can realize ZVS on the primary side in the entire load range and ZCS on the secondary side when the frequency more than FM and less than FS. The resonant network voltage is 0 when the converter works at the frequency equal to Fs and the efficiency reaches the maximum. Taking the converter working states as an example, the working process of the converter is divided into 6 stages. The operational circuit diagrams of different phases are shown in Figure 3, and the working principles are analyzed in detail. The working mode analysis of half-bridge LLC resonance converter is shown in Figure 3. The energy conversion of the converter is mainly completed by the fundamental wave in the Fourier series of voltage and current. At this time, the steady-state analysis of the converter only considers the fundamental components, and the error is tiny when the converter works near Fs. The AC steady-state model of LLC resonance converter in fundamental analysis is shown in Figure 4. And Figure 5 shows the relationship between the DC voltage gain and the normalized frequency Fn under different loads. The difference between the switching frequency F and the load value can be divided into 3 different regions, as shown in this picture. In order to realize ZVS on the primary side, the converter should be designed to work in Zone 2 and Zone 3. The relationship among the practical values of primary currents, capacitors, and dead time Td can be obtained as Formula 15. The secondary side current is the current transferred to the secondary side by the difference between the resonance current and the excitation current as Formula 16. Figure 7 and Figure 8, respectively, draw the graphics of the primary and secondary side current practical value changing from the equivalent capacitor CEQ and dead time TD by Maple mathematical software. It can be seen that under the condition of a specific dead time TD, the primary and secondary side currents have a minimum value, and with the increase of CEQ, the primary and secondary side current also increases. The experiment was accomplished and the data was analyzed. A half-bridge LLC resonance converter based on the Cascode gallium nitride HEMT with TPH 3206 PSB is built. It's tested under different load conditions, and the working waveforms of the converter are shown in Figure 11. The energy increases with the growth of the load, which is transferred from the converter to the load. The resonance current rises and the primary side cycle energy increases. The converter can realize ZVS at the primary side in the full load range compared with the hard switching applications. The peak and oscillation problems in soft switching applications vanish, and the stability of the converter is greatly improved. At the same time, the efficiency of the converter under different loads is tested. As shown in Figure 12, the maximum efficiency of the converter can reach 97% and the full load efficiency of 96.2% is achieved. In LLC resonance converter based on the Cascode gallium nitride HEMT, the device loss does not account for most of the converter loss, and the high-frequency transformer loss becomes the most significant part of the system under full load. Therefore, to further improve the converter's efficiency, it's necessary to use a planar high-frequency transformer to reduce the transformer loss further. The Cascode gallium nitride HEMTs are applied to LLC resonance converter with the soft switching topology. The relationship between daytime, primary, and secondary currents. The output capacitor is analyzed. At the same time, relying on the advantages of Cascode gallium nitride HEMT with small output capacitors, the soft switching conditions of LLC resonance converters is improved. The current of primary and secondary sides is reduced, the conduction loss and transformer loss are further reduced. The converter efficiency is improved. The hardware platform of 240 watts LLC resonance converter based on the Cascode gallium nitride HEMT is built. The maximum efficiency of the converter is 97%, and the total load efficiency can reach 96.2%. The loss of each part of the converter is analyzed, and the direction of further improving the efficiency of the converter is proposed. Thank you very much for watching my presentation, and don't be hesitant to contact with me by email. I'm glad to communicate with you. Thank you. Goodbye.